All right, so today we're starting Unit 2. We're learning about derivatives, and we are going to be in derivatives for a long time. Unit 2, 3, 4, and 2, 3, 4. Let me see, 5. 2, 3, 4, and 5 are all derivatives, so we won't get to integration until Unit 6. So we are going to spend a lot of time here. So this is what is the definition of a derivative and what are some of the basic derivative rules. And this is about 10 to 12% of the exam, right? Knowing how to evaluate a derivative. And these are the different things we're going to learn. This joke will make sense later, so I'll come back to it later. Today we are starting with, well, what is a derivative? What's the definition? See a little shadow here. Let me see if I can move over a little bit. Make it worse maybe. Okay, so we have to find the definition of a derivative, and we're going to do this with some graphs. So this is a linear function. Hopefully you remember that. If we had to find the slope of this line, we would just pick 2 points, right? Hopefully you guys remember how to do this. We're going to call the first one A. We'll call the second point B, which means that point is going to be f of A. And this second point is going to be f of b, right? So if you had to find the slope, hopefully you remember that that's just rise over run, which in this case you could find it like that, right? This should all be review. Or in our case, if we wanted to plug in what we had, the slope would be f of b minus f of a over b minus a. Right? Okay. Could we find the slope of this line if we were, say, had to find it at some point C? So I just picked a point C. How could we find the slope of this? This is not a line, it's a curve. So it's not as easy as this right here. So what could we do? Well, let me get it a different color and write this. Here's what we can do. We can approximate the slope of the curve at x equals c by evaluating the slope of the secant line. Hope you remember what that is. With another point near C. So we can draw a secant line between C and another point near C to approximate the slope. So it's going to be an approximation, right? So let's pick another point that's near C. I don't know. I'm just going, so here, if this is where C is, let's call, I'm going to leave a little bit of space because I'm going to draw and I want you guys to be able to see. So I'm just going to pick this point. Right? And we don't know what this is. This is C plus some change in X, right? This is some change in X here, but it's near C. Okay, and hopefully you remember what a secant line is. Let me get my ruler. A secant line, just a line that crosses the curve at 2 points. So this, I'm going to dot it, would be my secant line through the point C and C plus change in X. Okay, we also need to, we know that this is f of C, and we know that this is f of C plus change in X, right? Those are our y values. So here's the secant line. Now we are going to approximate the slope of the curve by finding the slope of the secant line. How would you find the slope of the secant line? Well, the same way you found the slope up here, right? The slope would just be rise over run, or change in y over change in x, however you want to write it. So what would the change in y be? Well, the change in y would be the difference from this point into down to this point. So it would be f of c plus change in x minus f of c, right? That's going to give you that distance, over c plus change in x, right? Minus c. That's going to give you this difference right here. Okay, so now let's simplify that. Can we simplify that some more? So if I rewrite this, I would end up with f of c plus change in x minus f of c. The top is still the same, but here I can do c take away c. That's going to be nothing, so all that's left on the bottom is change in x. So I could find the slope of this secant line by doing that if I knew all the numbers. Right? And so the key here, right, this approximation is going to be okay, but it's definitely not going to be perfect because you can see that the slope here of this line is not going to be the same as that curve. But if we narrowed this change in x till it was smaller and smaller, the smaller that interval is, the more exact our answer is going to be. So what I'm going to write down here is as the change in x approaches 0, right, as it gets smaller and smaller, we can find the exact slope at that point, x equals c. Right? So this one, we can make it smaller. I keep narrowing it so until it's infinitely small. What does that sound like if we're narrowing our window to make it infinitely small? Hopefully it's making you think of when we looked at the tables in our last unit on limits, right? The only way you could approximate a limit from the table is if that interval was infinitely small. So this is what we're doing here. We're going to be finding the limit so that this interval is infinitely small, the limit as it approaches 0, and that will give us the slope at any point along a curve, right? So this is getting to the definition of a derivative. So when you're finding the derivative, you are finding the slope of a function. This is key, at a point, right? So you're finding the slope of a function at a specific point. So in this one, we wanted to find the slope specifically at point C, right? So what we're really doing is taking the tangent line. Let me just use another color. Skip ahead a little bit. So you're really taking this, you're trying to find the slope of this tangent line, right? This line that only hits the curve at one point, at this point C. So here, we're really trying to find the slope of the tangent line. So that's my tangent line. Okay, but we're gonna talk about that later. So how do we do this? Well, we have to evaluate this as delta x approaches 0. So how could we do that? Well, we want delta x to approach 0, well, we're going to take the limit. So the definition of the derivative of f is given by the limit, and we're going to call it as h approaches 0 of f of x plus h minus f of x all over h. Okay? So this is the formal definition that uses the variable h. It is the same as the definition we put up here, which is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So this is the definition we found up here. I've just plugged in x instead of c, so you can find it at any point x. But the formal definition just replaces delta x with another variable h. This is the one you'll see more often. But if this one makes more sense to you, you can use it, right? This, of course, is provided that the limit exists. And for all x for which the limit exists, the derivative of f is a function of x. So we'll talk about this more. This f prime, or this f with the apostrophe at the top, is another way to notate the derivative of a function. So I'm gonna, that's actually our next page here. Pause it if you haven't written that down yet, because how do we write the different ways to notate a derivative? Construction is going on behind me, so I hope you guys can still hear me. So the different ways to write a derivative, this is equivalent to saying, like, you could show times multiplication like that, you can show multiplication like that, you can show multiplication with parentheses, right? Those all mean multiply. There's different ways you can show mathematically that you're talking about derivative. One is to say f prime of x. This is probably the most common. That just means the derivative of f of x. Another way you'll see it is dy over dx. That's showing the derivative of y with respect to x, means the same thing. Sometimes instead of equation saying f of x equals something, it will say y equals something. So in that case, you might see it as y prime. And then the fancy way, which you don't see that often, is like this. This just means the derivative with respect to x of f of x. So if something is telling you to find one of these, they're telling you to find the derivative. Okay, so let's actually find the derivative using limits. So here's our first example. Find the derivative of f of x if f of x equals 2x minus 3. So I'm not going to answer this yet. Well, actually, I'm going to answer it. So this is hopefully popping out to you that this is a linear function. So if I go back to my definition of a derivative, the derivative is just the slope of a function at a point. So a line has a constant slope, and this is already set up for you in slope-intercept form. So if this is slope-intercept form of a line, what is the slope of this entire line? Well, it's 2, right? mx plus b. So the slope should be 2. So if you had to find the derivative of a linear function, you would just find the slope, and that's your answer. But I want to prove or show you how you can use the limit definition to also get 2. So let's just write down the definition of a derivative first. The limit as h approaches 0 of f of x plus h minus f of x over h. All right, so there's the definition. So now let's plug in our function. So that's going to come out to, okay, so I'm not writing equals because this is my note of this is definition. Now I'm going to start the problem. So here we go. The limit as h approaches 0, f of x plus h. That means everywhere I see an x, I'm plugging in x plus h. So I have 2x plus h minus 3. That's this first part, right? Here we are. That's what I did to get this. All right. Now my next part of the equation is minus f of x. Okay, so now I'm just subtracting off the original function. So minus, and then 2x minus 3. So that's this part. Now to keep everything in order, I'm going to go ahead and just put a parentheses around this part and a parentheses around that part, right? So I know that I'm subtracting this function from that function. All over h. H is just h, so I'm going to put an h there. Now let's simplify that. So this equals the limit as h goes to 0 of, well, let's multiply this out. 2 times x plus 2 times h minus 3. All of that is take away 2x minus 3 still over h. All I did was distribute the 2 there. So let's keep going. Equals the limit as h goes to 0 of, all right, does anything cancel out here? Yeah, 2x, take away 2x, that goes away. Minus 3 minus minus 3 is negative 3 plus 3, that goes away. So all that I'm left with up there is 2h. And I still have h on the bottom. So now I can prove that this thing equals the limit as h goes to 0. My h's cancel out, of 2. And you notice each time I still wrote the limit because that's that proper limit notation I was talking about. And then what is the limit of any constant? What's the limit as h goes to 0 of the function 2? Well, that just equals 2. So that's our answer, right? So you could write this as f prime of x equals 2. That would be how you use the derivative notation from up here to write your answer. The derivative of x is 2. It's 2 everywhere, right? Because it's a linear equation. And then we can write that if it's the slope of this function is 2 everywhere because it is linear, right? Any point. So there's how that definition helps us find the slope. So let's do one that's a little bit more complicated. One that's not a straight line. All right, this one says to find the derivative of f of x if f of x is x cubed plus 2x. And it's saying find the equation of the tangent line through this point, 212. So they wanted to find it where x equals 2, right? Because this is not a linear function, so it's a curve, so it's going to have different slopes depending on what point you're at. The tangent line is going to have a different slope. So first, I'm going to just write the definition of a derivative over here. Okay, so now let's plug in what we know. The limit is h approaches 0. F of x plus h. Everywhere I see an x here, I'm just plugging in x plus h. So x plus h cubed plus 2x plus h. So that's the first one. Take away f of x as it is, so I'll just write it as it is, all over h. All right, so now let's solve that. So this whole thing now equals the limit as h goes to 0. Okay, I've got to cube this thing. So you can either write that whole thing out, or I'm just going to do that part here, right? It ends up being x cubed. So you can see when I did this the first time, I have all my notes up here of how to do that. So if you need to do that, if you need to work out x plus h cubed, you can. Okay, so you're working this out. Okay, but I'm not going to spend the video doing that. If you need to pause and do that and see if you get the same thing, go ahead. You end up with x cubed plus 3x squared h plus 3x h squared plus h cubed plus 2x plus 2h. And then this whole thing is minus still x cubed plus 2x, right? And all of that is still over h. Okay, so now let's do some simplifying. So if I look, pencil go. All right, so if I look, I can start to see that this x cubed, take away that x cubed, goes away. Plus 2x, take away 2x, also goes away. And I think that's it, right? None of this is going to go away. So let's rewrite what we have. Still have to write my limit notation. I end up with this. Okay, so now hopefully you can see I have an h in every term and I have an h in the denominator, so I can start crossing these out. This h cancels with that h. This h turns this into an h squared. This h makes this just a regular old h, no exponent. This h cancels out with that h. So now, if I rewrite, this is the limit as h goes to 0 of 3x squared plus 3xh plus h squared plus 2, right? So that's what I'm left with. Now I'm at this point in the limit where I don't have a fraction, so I'm not worried about plugging in 0 and having a 0 in the denominator. I can actually plug in 0 and see what the answer is. So 3x squared plus 3x times 0, right? Because h is 0, plus 0 squared plus 2. All right. So this means that I am left with 3x squared plus 2, right? Because all these go away. So I've just found that the derivative of f of x, f prime of x, is equal to 3x squared plus 2. I've just found the equation that is going to give me the derivative at any point. But now I need to find it for this specific point when x is equal to 2. So at x equals 2, I'm just going to plug in 2. F prime of x equals 3 times 2 squared plus 2, which is equal to 3 times 4, 12, plus 2, so that whole thing is 14. So what we would say here is the slope of f of x at x equals 2 is 14. Or the other way you can say it is that f prime of 2 is 14. They say the same thing. The slope of the function at x equals 2 is positive 14, or actually the slope of what you should really write here, the tangent line. The slope of the tangent line of f of x at x equals 2 is 14. Or the fast way to say it would be f prime of 2 is 14. The derivative at 2 is 14. Okay, so before we end, I wanted to give you another way that you might see this definition of a derivative. So we use the first definition where there's h's. Another way you'll see it is that like this. So it says an alternative definition of the derivative is written f prime of c is equal to, so the derivative at c is equal to the limit as x approaches c of f of x minus f of c over x minus c. Okay, so this is just telling you to find the slope at point C. So I'm just showing you that sometimes you'll see it in other textbooks and documents it's written like this. This definition is based on the formula for slope, right? Just like ours was. And the derivative is calculated, is the calculated slope between 2 points that are infinitesimally close together. And so the existence of this alternative form requires that, for this to be true, just like for any limit to be true, the left side of the limit has to equal the right side of the limit, right? They have to both exist, they have to both be equal. Otherwise, there can be no derivative at C. So there will be times when the derivative does not exist, right? Just like there are slopes that do not exist, okay? But we'll talk about that later. Today you're going to practice using this derivative definition. See you next time. Sorry for the long video.